Welcome to the deep dive. If you need a shortcut to being well informed on some of the thorniest climate challenges, you are definitely in the right place. Today, we are digging deep into the sophisticated computer models that predict the future of carbon in our soil. And this isn't just about dirt. This is really about the difference between theory and reality in climate accounting. Our sources, which are a fascinating stack of research papers, are going to give us the critical knowledge we need to understand the mechanics behind soil organic carbon, or SOC sequestration, and of course, the very messy dynamics of key greenhouse gases, QO, N-Euro, and CH. But critically, we're going to zero in on how these models cope when we introduce large-scale carbon dioxide removal technologies.
Like feeling like biochar and enhanced rock weathering.
Exactly.
And it's such an essential deep dive because, models, they're not just calculators. They're more like scientists trying to wrestle with this incredibly complex interplay of soil chemistry, microbial biology, physical laws, all at the same time.
Right. So for you, the learner, the goal here is to understand not just what the models predict, but why predicting something that seems simple, like a sudden spike in N-Euro emissions after a summer rain, is still one of the hardest things we do in climate science. And that gap between prediction and reality, it has real implications for climate policy, for investment. And we'll synthesize why different models are built for different jobs and why choosing the wrong one can dramatically skew your climate outcome.
Okay, let's unpack this. Let's start with the blueprint of soil prediction because our sources show there are really two fundamental classes of models that you need to know about.
And understanding what they're for, their mandates, is key.
So first, you have what we can call the long-term accountant models. These are the SOC turnover models. They're focused primarily on long-term SOC sequestration and storage. They are, you could say, CO-centric.
Meaning they're designed to track carbon moving in and out of the soil over decades, maybe even centuries.
And the big names here, think RothC and ICBM. RothC is very robust. It uses a detailed multi-pool structure, so it divides SOC into different types of carbon with different decay rates.
Which means it's great with long-term data.
Exactly. It handles long-term experimental data beautifully. ICBM, on the other hand, is popular because it's simple. It's just much easier to calibrate.
So, okay, they're great for tracking long-term storage, but what's the catch?
Well, the catch is they are focused on the carbon budget, not the full climate budget. They have very limited or even no explicit features to simulate those really powerful short-lived gases like nitrous oxide, N-Euro, and methane CH.
So when you need the full picture.
When you move beyond simple accounting and you need to see the full climate picture, you need something far more complicated.
And that brings us to our second class, the real-time chemists. The integrated biogeochemical models. These are essential for the detailed emission inventories, what we call Tier 3 accounting, and for analyzing comprehensive GHG reduction scenarios.
Right, these are the heavy hitters. DayCent, DNDC, APSIM, IPIC, and EcoSys. They integrate the carbon and the nitrogen cycles explicitly.
And the difference in the models, it comes down to what's happening under the hood, right?
It does. It comes down to the fundamental rules they use to govern how fast things decay and transform.
So what is that difference, mechanically speaking? You mentioned kinematics. For someone listening, what does that mean in this context?
Essentially, it's the rules of movement and speed. The majority of these widely used models, like RothC and DayCent, they rely on a first-order kinetics approach.
Okay.
Think of it like a speed limit that's based only on the concentration of the carbon itself. So if there's more carbon in a pool, it decays faster, regardless of external conditions. It's effective, but only for general long-term trends.
That sounds like a gross simplification of a dynamic living system.
It is.
Yeah.
And that's exactly why you need the mechanistic models like DNDC and EcoSys. These models don't just use first-order kinetics. They explicitly reflect the soil's physical state.
What does that mean, physical state?
It means they look at real-time conditions. Things like aeration, how much oxygen is in the soil, and redox potential, which is absolutely crucial for modeling nitrogen transformation processes.
Especially the ones that lead to NRO.
Exactly. They act more like a real soil chemist would.
Okay, here's where it gets really interesting, especially if you're relying on these model outputs for policy or, say, carbon credit valuation, the NRO prediction problem. Why is that tiny molecule nitrous oxide, which is nearly 300 times more powerful than CuO over a century, such a major pain point?
Because NUO is a byproduct of these complex microbial processes, nitrification and denitrification, and they are incredibly sensitive to water and temperature swings.
So the models just can't agree.
Well, the mismatch comes from differences in how they handle these rates, the final N-to-N-RO emission ratio, and especially how gas physically diffuses through the soil. And crucially, the results can vary wildly, even under identical conditions, just because of different mathematical functions related to two factors: soil, water-filled pore space, or WFPS.
Which is basically how wet the soil is.
How wet or oxygen-started it is, yeah. And temperature. That is the sensitivity factor at play. If the model uses a different formula to link soil wetness to NERO production, you get a completely different answer.
And this leads to the most critical limitation that our sources flagged, the underestimation problem.
Yes, the models frequently miss the major event-driven peaks in NERO emissions. These aren't slow leaks.
No, these are bursts.
They're sudden bursts of activity right after a major disruptive event, a huge downpour, fertilizer application, or the critical and often overlooked phenomenon of freeze-thaw cycles.
Wait, so if the models are missing the spike, the cumulative total is too low, right?
Oh, absolutely. There are studies comparing models like DayCent, DNDC, and EPIC in, say, dairy farm scenarios, and they show this clearly. You miss the spike, you miss a huge chunk of the climate impact.
And if carbon markets or GHG budgets rely on those totals.
They could be significantly overestimating the climate benefit of certain practices. And that's the massive policy consequence of what seems like a small technical flaw.
That really helps explain why selecting the right tool for the job is so vital. So let's summarize the selection criteria. If you're just interested in long-term SOC trends, you stick with the accountants.
Right, RothC or ICBM, because they have minimal input requirements.
But if you're trying to analyze the granular short-term management effects, like how fertilizer or tillage impacts NERO,
you must use the real-time chemists, DayCent, DNDC, EPIC, or APSIM.
And what about that challenge with freeze-thaw cycles?
If you're studying cold climates, and you really need to accurately account for the thermal and water physics, the physics of freezing and thawing, then COO model is the one that specializes in that precise physical process coupling.
Okay, so if that's the current complex state of soil modeling, let's look at how researchers are forcing these models to account for entirely new inputs, starting with biochar.
Biochar.
Right, the stable carbon produced by heating biomass. It's essentially a carbon sponge you bury in the ground.
And the climate benefits are, on paper, very clear. A long-term SOC increase and GHG suppression. But you can't just treat it like normal dead plant matter. You have to account for its unique structure.
So how do we modify the models?
Well, existing models are modified primarily to address two unique characteristics of biochar. First is its high recalcitrance, its extreme resistance to decay.
This isn't carbon that breaks down in a few years.
No, we're talking about carbon that persists for centuries, unlike native soil carbon, which might decay in decades. And second, we have to model this interaction with the SOC that's already there. So researchers modify models by adding dedicated labile and recalcitrant pools specifically to simulate that long-term residency.
Can you give us a concrete example of a modified model?
The modified RothC is a perfect example. By adding those extra pools, it can simulate the biochar's longevity, and it can also simulate something called the priming effect.
Explain the priming effect simply for us.
It's a bit counterintuitive. It means adding this new, fresh carbon can sometimes stimulate the existing older carbon pool to decompose faster.
So you're adding carbon, but you're also causing other carbon to be lost.
Think of it like adding fresh kindling to a dying fire. The kindling burns, but it also makes the old logs burn harder. When that old carbon burns faster, it means a short-term risk of increased co-euro emission. It's a modeled trade-off.
So you gain long-term stability, but you risk a temporary co-euro spike. That's really important for policymakers to know.
Absolutely. Another excellent modification is the APSIM-Biochar module. APSIM is used heavily for cropping systems, and this module is uniquely engineered to reflect biochar's influence on the soil's physical properties.
Like water retention.
Exactly. Water retention, density, things that impact crop yield and overall soil function.
And what about those tricky nitrogen and methane dynamics we talked about earlier?
For those, you might turn to the DNDC-BC, which is a modified version of DNDC. Because DNDC is one of those mechanistic real-time chemists, it's specialized for predicting NERO reduction and crucial CH dynamics.
Which would be important in what kind of environment?
Particularly useful in specific waterlogged environments, like paddy rice cultivation, where methane is the dominant gas problem.
And finally, for the highest fidelity, most detailed simulation.
For that, you'd use a high mechanistic approach, like Biochar. Biochar explicitly simulates complex microbial processes, including the physical adsorption and desorption mechanisms.
Where the carbon literally sticks to mineral surfaces.
Exactly, taking it out of the biological decay loop entirely.
So, synthesizing this biochar analysis, we confirm the long-term SOC benefit. But what's the big cautionary takeaway for the listener?
The big cautionary takeaway is the variability. While N-Euro and CH generally decrease, the sources emphasize that the net climate effect is highly variable. It depends entirely on three factors: the specific type of biochar used, the characteristics of the receiving soil, and the local climate.
If you don't model all those interactions, your prediction is weak.
Very weak.
Variability is certainly the rule, not the exception, in CDR. Let's move to our second strategy, enhanced rock weathering, or ERW. This is an inorganic carbon removal method applying finely crushed silicate rocks, like the salt, to accelerate natural weathering.
Right, the rocks dissolve, they absorb co-yaws from the atmosphere and eventually lock it away as bicarbonate. But ERW presents a distinct and perhaps even greater modeling challenge than biochar.
Why is that?
It's like trying to model a chemistry lab and a biology lab with the same software. The core difficulty is that ERW modeling is still in its early stages because existing models struggle to sufficiently link the inorganic weathering reactions, the rocks dissolving, with the established organic carbon cycling models.
So the rocks are changing the chemistry.
And that changing chemistry is affecting the living microbes.
Exactly.
We see this challenge even in the global land surface models like the modified CLM5. This model simulates basalt dissolution and the resulting key factor, soil pH changes. They then have to couple this pH change asynchronously to the nitrogen cycle.
So the changing pH is the critical link between the inorganic rocks and the organic greenhouse gas emissions.
It is. And the primary indirect effect they model is powerful. The pH increase is estimated to inhibit the processes of nitrification and denitrification.
The processes that produce N-Euro.
Exactly. This could lead to a significant 18% reduction in global agricultural N-Euro and NO emissions. An 18% reduction globally is a massive number to hang on just a pH shift.
That is a staggering potential climate win. But we've learned in this deep dive that every major intervention seems to have a trade-off. What's the risk with ERW?
The sources flag a concerning side effect: the potential for an increase in ammonia volatilization.
So you solve one problem and create another.
Potentially. By making the soil more alkaline, raising the pH, you suppress the processes that create N-Euro, but you simultaneously increase the conditions that drive ammonia gas to escape the soil. It's an atmospheric trade-off.
Right, you reduce one greenhouse gas, but you risk increasing another airborne pollutant.
And for researchers who need to model the precise geological and chemical reactions, not just the large-scale climate effects, which tools are they using?
That would need something much more detailed.
It requires the high-detail perspective of reaction transport models like CrunchFlow. These models focus on detailed, multi-component geochemistry and microbial processes, right down at the grain level, and they reflect the primary goal, which is bicarbonate formation for inorganic sequestration, but they also model a specific, localized adverse effect: the risk of transient SOC loss.
Transient SOC loss, is that similar to the biochar priming effect we discussed?
In principle, yes, but for different reasons. When you rapidly change the soil chemistry, the sudden availability of chetations and the shift in pH can temporarily stress the microbial life. This increases microbial respiration.
Causing them to exhale a brief, temporary pulse of co-row.
Exactly. The models show it's a temporary effect, but it's a necessary consideration for the net carbon budget.
So, summarizing the ERW modeling takeaway, it enhances inorganic carbon sequestration. Models predict a strong potential to reduce N-Euro via pH effects, but the net benefit is highly context-dependent on soil and climate. And there's a modeled risk of that temporary CO-Euro and the competing risk of ammonia volatilization.
It is ultimately a chemical balancing act.
This entire deep dive has reinforced a few core insights for you. The models reveal that CDR is a precise chemical and physical balancing act. It's defined by strict decay kinetics, these event-driven peaks, which are often missed, and incredibly complex interconnections between carbon, nitrogen, and soil physics, like water content, temperature, and pH.
And the overarching finding from these sources is that the true effectiveness of both biochar and ERW is acutely dependent on local context, soil type, climate management practices. We saw how different models had to be modified just to capture these nuances.
So for global policy,
For global policy and investment, achieving reliable large-scale prediction requires major continued efforts in model harmonization. We need the DayCents and the COO models of the world to agree on the fundamentals if we're going to trust the global climate math.
that need for harmonization is key. And for you, the learner, here's one final provocative thought to mull over. We spent a significant amount of time discussing the N-Euro prediction problem. We noted how sensitive the most accurate models, like Key Model, are to freeze-thaw cycles, and how the major N-Euro peaks occur and are often missed during those events.
So if climate change means we face a future with fewer consistent hard freezes and more frequent inconsistent thaw events throughout the winter season, more unstable, disruptive weather patterns, consider this. What might that continuous volatile disturbance mean for the global N-Euro budget?
Could that seemingly small, unpredictable shift in winter weather potentially overwhelm the hard-won N-Euro reductions we've so carefully modeled for enhanced rock weathering and biochar? It's a reminder that the models are only as good as the future physics we feed them. Something to think about as you connect the complexity of soil chemistry to the simplicity of the weather forecast.
That's it for this deep dive. We'll see you next time.